All right, so lesson 24 out of 26, solving trigonometric equations. Okay, so in the last couple of days, we've talked about a lot of different trigonometry stuff, right? One of the things we talked about were the identities, okay? And so things like, cosine squared plus sine squared equals 1. That was one of them. We had, double angle identities. So if you had a double angle, 2x inside, that could be rewritten as 2 sine x cosine x, right? And there's a variety of identities, okay? Well, one of the reasons why we learned these identities is because it makes it easier to solve trig equations, okay? And so we'll go ahead and do a few of them now and talk kind of about how you write out the solutions, because that's really the tricky part, writing out the solutions correctly. Let's go and talk about this really quick. So this looks kind of crazy. Let me dissect it for you real quick. So on the circle, right, when we're trying to find our solutions here, we have a point for any given point. Let's say this one right here. We have an x value and a y value, right? Well, it's possible, it's actually probable, almost every x and y value occurs twice, right? Here's a positive x, the y is negative in this case, but there's a positive x value right there. And so notice there's two separate angles here and then here that give you the same x value. So there's usually two instances, okay? And so what you could do is find the first one. This is a shorthand if you don't want to do the whole circle. There, find the first one, whatever means you have to. And then if you do 2 pi minus that first one, you get your second angle. And you can kind of see that here just looking at this one. If this one, let's say, was our first angle, then our second angle would be 2 pi minus our first angle. So we took away our first angle, that would bring us to our second one. Okay, and the same thing is true with sine. If you subtract it from pi, you get the second one. And tangent, if you add pi to it, you get the third one. Okay, or you get your second one there. Okay, also, notice this plus 2 pi k. That's important. That just accounts for all the possible rotations. So let's say you landed here, and this was the x value. Well, if you added 2 pi, a rotation, that gets you back to that value again. So it's another angle that gives you the same value, okay? And you can rotate it again and again and again, and you can get an infinite number of solutions there, right? An infinite number of angles with the same x value. And so, okay, keeping that in mind, we'll add 2 pi k. K, by the way, I mentioned it this morning. K, this notation just means k is in the set of, or it belongs to, integers. So in other words, k is 0, +1, -1, +2, -2, and so on. So basically, you have 0 rotations, 1 rotation, a rotation in the other direction, 2 rotations, 2 rotations in the other direction, and so on. Okay, so don't let that notation surprise you. It is just a way to say all the additional rotations, an infinite number of solutions. Okay, so that's what k represents. All right. Let's start off with a pretty straightforward one here. Sine of 2x is equal to 1/2. So what you want to do is think about this statement here. Sine of theta is equal to 1/2. Okay, well, if I picture my circle, my unit circle here, sine is 1/2 here at pi/6. Sine is 1/2 here at 5 pi/6. Okay, those are my two cases where sine is 1/2. Okay, so I'm going to actually write that out. My first angle is pi/6 plus all the extra rotations, right? So again, that pi/6 accounts for this first point, but remember, you could possibly plug in another rotation, another value that's just a rotation away. It actually would be 13 pi/6, which would give you the same value. So that's two different inputs. Okay, so 2 pi k accounts for all the extra rotations, and then theta 2, our second angle, is 5 pi over 6 plus an infinite number of rotations, right? Because you can have more rotations. Okay, so this is a good setup. What I'm going to do now is say, okay, in this problem, I was not given theta. Instead, I was given 2x. So I'm going to say 2x equals pi over 6 plus 2 pi k. Pi over 6 is 2x is equal to pi over 6 plus 2 pi k. And then I'm going to divide everything by 2. And I'll write that step out, especially since this kind of gets a little, I guess, convoluted if you're not used to it. The 2's would cancel. So x equals, we talked about it this morning, if you have a fraction on top of a number, like an integer, just multiply those two numbers together. 6 times 2 is 12. So we have pi over 12. Multiply the two denominators. And then those twos cancel to leave me with pi k. Okay, so that's one set of solutions. That's pi over 12 plus rotations. So if I added a rotation by pi, that's half of a rotation around the circle. That would be 13 pi over 12. And then if I added another one, that'd be 25 pi over 12, and so on. It would go on and on and on. Okay, that's what that means. I'm not going to leave that there, though. Okay, so there is one set of solutions. Let's talk about this one here. So 2x is equal to 5 pi over 6 plus 2 pi k. Again, I'm going to divide everything by 2 to get x by itself. And again, I'll get pretty much the same thing, except with a 5 in front of the pi. Okay, so those would be my solutions together. Pi over 12 plus pi k. 5 pi over 12 plus pi k. All right, let's find all the solutions to this equation right here. Cosine of x plus 5 pi over 6 equals 0. We'll set it up exactly the same way. We're going to think about this. When is cosine equal to 0? And it equals 0 at two places if I think about the circle here. The x value is 0 and we hit pi over 2. And also when we're at 3 pi over 2. Plus every additional rotation. Okay. Now from here, I'll look, this is actually theta, that inside piece. So I'll say x plus 5 pi over 6 equals pi over 2 plus 2 pi k. Same thing here. And here I'm going to subtract 5 pi over 6 from both sides. So that I get x by itself. Pi over 2 minus 5 pi over 6. I need to write that something over 6. So I will actually just multiply it by 6. Nope, not 6, by 3. I'll turn that into a 6. So 3 pi over 6 minus 5 pi over 6 is negative 2 pi over 6. Or negative pi over 3, of course. Notice it did not affect the rotation because you're subtracting it, right? If you were multiplying or dividing, then it would. Okay, same thing here. I still need the denominator to be the same, so I'll multiply the top and the bottom by 3. That'll give me 9 pi over 6. Nine pi over 6 minus 5 pi over 6 is 4 pi over 6. Reduce that. Okay, there's one more thing to do here. Typically, the way you write these out is you want your numbers, right? Your first angles, your initial angles to be within the first rotation at 0 to 2 pi rotation. Okay, well, negative pi over 3 is not. 2 pi over 3 is fine, but negative pi over 3 is not. So I need to find a coterminal angle. In other words, I want to find that exact same angle, except get it to where it falls between 0 and 2 pi. Okay, that's the same thing as 6 pi over 2, right? I mean, over 3. 6 pi over 3 is the same thing as 2 pi. So we're adding a rotation. So there we go. Okay, so 2 pi over 3 plus 2 pi k and 5 pi over 3 plus 2 pi k. Again, remember, all that happened there is that this negative pi over 3 is this point right here. Well, negative pi over 3 is not within the first rotation, right? Whenever you start at 0 and you go all the way around and return, and it's 2 pi. So to get it within that first rotation, I added 2 pi to it. And it goes all the way around and come back. And that's where you get 5 pi over 3. 5 pi over 3 and negative pi over 3 are the same thing. I did not have to rotate this one because 2 pi over 3 is here. And that's between 0 and 2 pi. That's on the first rotation. Okay, so 2 pi over 3 plus 2 pi k, where k is that integer, or 5 pi over 3 plus 2 pi k. And that'll cover all of my values. Okay, let's solve this one. Cosine squared of x is equal to 1/2. Okay, obviously I want to get cosine by itself, so I'll use the square root property. I can do that here. So cosine of x is equal to the square root, positive and negative, the square root of 1/2, or the positive and negative square root of 1 over the square root of 2, which happens to be positive and negative 1 over the square root of 2. And I can't leave that square root of 2 in the bottom here, considered improper, so I'll multiply the top and the bottom by the square root of 2. And what does that give me? Square root of 2 on top, 2 on the bottom. So I'm looking for all of the angles where cosine, the x value, is square root of 2 over 2 and negative square root of 2 over 2. Which, if you think back to your unit circle, that's actually not too hard to do, because here we have square root of 2 over 2 at pi over 4. Here we have it at 3 pi over 4. Here we have it at 5 pi over 4. 7 pi over 4, and so on. So it goes around and around and around. All right, and so instead of writing out this as 4 separate things, right, I could do that. Instead of doing it that way, I'm going to do it a shorthand way. Think about the distance, right? So from this point to this point, that is 90 degrees, a fourth of a circle. From this point to this point, there's another 90 degrees, or pi over 2. From this one to this one, Notice I'm just adding pi over 2 to get to the next point over and over and over again. So instead of saying that it needs to be 4 individual ones with plus 2 pi k, I can actually capture all of them by saying that x is equal to pi over 4 plus pi over 2 k. That'll cover all of them. If I add pi over 2 to this one, I get this one. Add pi over 2 to that one, I get this one, and so on. I keep going around and around and around. All right. All right, so the next few problems that we're going to do involves those identities we talked about earlier, okay? So here we have cosine squared x equals 2 plus 2 sine x. Notice we're told to just find the solutions between 0 and 2 pi. So we don't really have to worry about the k thing, okay? The 2 pi k, the extra rotations. So that's kind of nice. So anytime you see cosine squared or any kind of trig function squared, you should probably think of the Pythagorean identities, especially this one. Okay, because that by itself is not very helpful, but if I subtracted sine x squared from both sides, I get this, which that one actually is helpful because I can use substitution. I can replace cosine squared with 1 minus sine squared. Okay, well, this is setting up to be a quadratic. It's a little uglier, but we can work this out. Add sine squared to both sides. And we're going to subtract 1 from both sides, so I get plus 1 on the end. Now, maybe that looks confusing, right? Imagine this said x squared plus 2x plus 1. I don't want to spend a lot of time factoring this, okay? So I'm going to go ahead and factor it quickly. You can always look back on when we factored other things. But if you think about it like that, you get sine x plus 1 times sine x plus 1. The zero product property, right? So set each of them equal to 0. I'm only going to set one of them equal to 0 because they're the exact same thing. So I'm looking for where sine of x is equal to -1. Okay, well, in the circle here, sine only equals -1 down here, right? At 3 pi over 2. Only once per rotation. And since I'm asked to only find the solutions that are within one rotation, I only have one solution here. Okay, same thing. This time though, instead of having a Pythagorean identity, here's a double angle identity. Cosine of 2x equals 5 sine x minus 2. Okay, cosine of 2x, there's a few options for double angles for cosine, but the one we're going to use here is 1 minus 2 sine squared x. The reason why I want to use that one is because it only has a sine, and if I replace that, then I'll have sine on the left and sine on the right, and that'll be the only trig function that I'm working with. Just sine. Okay, so let's add 2 sine squared x to both sides. So it's positive. We have a positive 5 sine x. -2, subtracting 1 from both sides will give me a -3. So 0 equals 2 sine squared x plus 5 sine x minus 3. I'm trying to hurry here, so I'm going to go ahead and quickly factor it. Remember, you could think about this as 2x squared plus 5x minus 3, in which case you would get 2 sine x. I think it's -1 right here, and then sine x plus 3. That's my guess, at least. Do a quick check to make sure I'm right here. I know that'll multiply to be 2 sine squared. I know that'll multiply to be -3. There's negative sine x. That's positive 6 sine x. If I added those together, I get 5 sine x positive, which is what I have here. Okay, so it works out. I factored it correctly. Okay. Let's set them equal to 0. On the left, if I add 1 to both sides, I get 2 sine x equals 1. Divide both sides by 2, and I get 1/2. On this one, I subtract 3 from both sides, I get -3. Oh, too many negatives. Okay, so on the unit circle, sine is 1/2 at pi over 6 and 5 pi over 6. Sine equals -3 nowhere, right? Because here's 1. Here's -1. -3 would be down here somewhere. The circle doesn't touch that, right? So actually this piece right here is without a solution, right? So that one has no solution. So I only have 2 solutions, pi over 6 and 5 pi over 6. All right, and that would do it for this lesson.